Okay, so this is just sort of more kind of advanced harmonic oscillators, right? So let's just go back and I'm not going to go through everything again, obviously, but I do want to start a little bit behind where actually I don't know if this red shows up on the video very well. So,
I think it goes better with black.
but yeah, black would be good. Yeah, I asked them to give me better markers because it doesn't. Yeah, there's that glare. Well, that'll be good enough. Yeah, some of it'll be cut off. That'll be fine. Okay, so of course we start with the differential equation, right? This is how we get the harmonic oscillator at all, right? This is a differential equation, but it's all just F equals ma. So remember yesterday, Professor Z kept saying, all I'm doing is solving F equals ma or whatever. So that's actually a good way to think of it. It's not normally when people say all we're doing is X, and it's something really complicated. Sometimes that's not a very helpful thing to say. In this case, it actually is because it looks like we're doing a separate thing that's separately physics and not related to like kinematics and stuff we've been doing. But really, all we're doing is doing F equals ma, where F, I really should put ma equals F because this is F and this is ma.
Yeah.
All we're doing is this, where F is actually proportional to something else in the system, another the parameter X, the position. And the only reason that we could do F equals ma before and not have to worry about differential equations is because they were sort of easy differential equations. So normally if we have like gravity, F equals mg,
Yeah.
right? The differential equation would really be like this. This is still a. And now this is actually constant. So this is a differential equation. It's just sort of simple because you take two integrals and all you get from this is all of the like d equals 1/2 at squared, right? Plus vit. Like all of these things are just from this differential equation. So we could just use the results. We don't need to like solve it each time or whatever. And in the same way, it's the same way here. It's just that now, of course, our solutions are actually a little more complicated. They're not sort of just constant. Acceleration is just the derivative of velocity. It's not just like that. I mean, that's true always, but it's not just acceleration is not a constant. Is what I'm trying to say. Because acceleration is not a constant. Another way of saying that is that this is not a constant, right? Because this is acceleration. This part. This is not a constant. This means that the differential equation. It's always been a differential equation, but now it becomes more complicated. And now, through the ways we talked about in the last office hours and stuff, it's all just it's a math problem to now solve the differential equation. And we know the solution, so I'm not going to go through it again, but it's just basically this, right? Cosine omega t plus phi. This is my favorite way to write it. Of course, we saw there's many ways to write it. You could write it as the real part of an imaginary exponential. You could write it as a cosine, or just a single sine wave with a phase that lets you adjust. So that was one of the questions, right? Just the phase, all it does is move you left and right, sort of where do you want to start t equals 0? Because when you plug in t equals 0, if you didn't have this, you would have to get cosine of 0 is 1, and that's sort of, it's restrictive. You don't want to necessarily have to start at 1. What if you want to start at 0 or some other random time? So this allows you to use your initial conditions, and so does this. Sorry, I've introduced the new variable omega naught. Oh, sorry, the other way, the third way to do it would be to do a cosine and a sine, and of course then we wouldn't need this phi, because to shift it we could just use different combinations of sine and cosine. This is, I think, the clearest way to write it, because these are physical interpretations. This is not a new parameter. This is not fixed by initial conditions. This is just another way to write the things that we have in our equation. And so if you plug this in, and we saw you'll get, if you literally plug this equation into here, you can do it with any of the forms that we had, you will get that omega naught squared is k over m. And it was positive k over m. This minus sign was, if we plug it in, we'll see that taking two derivatives of the cosine gives us a minus cosine, so that's where the minus sign goes. So this is not there's no imaginary numbers or anything like that in here. This is just omega squared, naught squared. I'm defining omega naught to be this. It was k over m. Now the reason we do this and we don't just write k over m here all the time, which is sort of the normal thing we do, is because in a wave, the number that multiplies the t has a better interpretation as opposed to just some number. It's not just k over m is some number, right? This has or spring constant over mass, whatever. That's not in a wave, this is actually has a meaning. Omega naught is the angular frequency, right? And we saw, so this actually has, there's basically two different places. One place is, we know the solution looks like this. There's a parameter omega naught, which must be the angular frequency, which we can relate to the period and all that stuff of the wave going up and down. But we also see that it's equal to this thing that has nothing to do with waves as far as we know. It's just the mass of the block and the spring constant. So it's kind of an interesting relation that this happens to be the required relation that we get, and it relates like this side is just measurable properties of a block or whatever, and this side is about a wave. But the block moving in a wave happens to give you this relation. Now, of course, if we saw, if you add, let me just remind myself with the, in parallel, okay. I don't want to get too far off and just repeat everything I said, because I like talking about it, but of course, I know not everyone wants to hear about it much times. If we have something, I'm using mixed notations. If we use this, now of course we saw that this, they don't use B in the book, they use M gamma, where M is still the mass. The only reason they use M gamma is because you'll see that if you plug it in, you'll get, if you plug it in, you'll end up having to divide by, like you'll see if you divide everything by M in this equation, you get K over M, which we know is omega naught, but then you'll get just gamma by itself. So it's just a convenient choice to call it M gamma. Doesn't mean anything physically. It's just this. You could call this B if you want. That's what I just did. Sometimes they do. Anyway, so this is a damping force, and we saw that when you plug in this same equation, so when you plug in the same, this still solves. Actually, sorry, this doesn't solve it. I'll simplify it a little bit because we know that it's really the real part, and you have to use the exponential or whatever. It's really, and in the book they call it D. D is just the same as A. It doesn't matter. E to the minus gamma over 2. Now we saw literally in the, or maybe it might be squared over 4. Well, I'll leave it like this. This might not exactly be correct, but it has a negative exponential. This is a real exponential. This is a decay, right? E to the I something is not a decay. It's an oscillation, right? It's a cosine sign. But e to the minus real number, that's a symbol for real number, is a decaying exponential. So that's good. And we know that this type of thing, we saw it in the last homework, that you could solve for which, if you put it all in one, and then you could actually solve for what omega is, and it happens to be like, what is it, something 2 gamma omega or something like that. This was some equation that he used. This omega naught is K over M again, so I like calling it omega naught. This is a confusion a little bit in the book. They change notation, and it's kind of annoying. In the lecture last night, I believe for the entire lecture he used this notation, where omega naught is always the K over M, just K over M, as if it's undamped. So it's like a sort of a pure oscillator. Omega naught is always the pure version of the oscillator. And of course, as gamma goes to 0, omega becomes omega naught, right? Whereas omega is the actual frequency, and you know it's the actual frequency because it appears in the cosine. Or whatever appears here is the frequency no matter what, right? And so this is actually omega naught, my natural sort of free frequency, minus some amount, right? And now this is an equation you'd have to use to solve for omega. You'd have to use the quadratic formula, and you get something with square roots or whatever, and you can plug it in, you get something like this or whatever. But if you plug it into the imaginary exponential, all that stuff. So anyway, this looks like, well, when we multiply two functions, it's sort of, I don't want to say something that's too specific, and I don't want to say something that's too general. Because we're multiplying these two functions, we can think of, so forget about D, pretend D is 1 for now. This equation is bounded by 1 and minus 1, right? So whenever we write cosine of something, this goes as a maximum, the height of this goes to 1 at some points, and the lowest point goes to minus 1. But of course, if we multiply by some coefficient, then the height becomes that coefficient, and the lowest point becomes minus that coefficient. But the coefficient is actually, sorry, there should be a t here, because it's time. Yeah, this exact mistake I made in the last one. So if the height is now dependent on time, well, what does this function look like? We know it's a decaying exponential. you'd have to actually plot it, but there's some things like when t equals 0, it has to cross 1 and all this stuff. So pretend, again, d is 1 for now. And then the lowest point would have to be minus this whole coefficient. The whole coefficient, again, is that function. So it's that. And then we know that this oscillates between this amplitude effectively. And of course, this amplitude is now sort of time dependent. That's just one way to think of it. That's not actually like a true, the amplitude is, technically the amplitude of this is just supposed to be d, but I'm calling the amplitude of the cosine anything that multiplies the cosine. Just it's a way to think of it, I think. Anyway, so now I'm not going to draw, it depends on the phases, I guess, but I'm not going to draw it lined up right. But then we get something that looks like this. Now this, of course, as t goes to infinity, this exponentials go to 0, right? And so this wave is just going to oscillate like this. The difference between this and the free one is not just that it's squashed. It's not just a squashed normal wave. It's actually, this omega is not omega naught. So because there's some damping, this is actually going to be a smaller frequency and therefore a longer period. So this t is actually a little bit longer than if it was free. So it's not just squashed, it's also sort of spread out a little bit. Anyway, you can think of that as the oscillator if it had no damping, it would just sort of freely bounce back and forth between the endpoints. But because it's being slowed down a little bit, it's still going to be an oscillator, right? It's not like the oscillation is affected that much. I mean, the amplitude is, but it still looks like a cosine wave, but it's actually a slightly longer cosine wave because it's sort of being slowed down on the way up and the way down kind of thing. So it's just a little bit slower. Anyway, sorry, now I'm kind of continuing to get off track and not talk about the actual question. So what is the effect on the resonant frequency? Okay. So let's think about springs in series and parallel first, because that's what the question is asking. The question is asking, let me just say one more thing. The question is asking about resonant frequencies. So I'm going to erase this, if that's okay.
Yep.
So the question is asking about resonant frequencies. So the only time you'd have a resonant frequency, when they say that, they don't say anything what's the situation, but we know that there must be a driving force. Because to have a resonance means that there's two frequencies that are lined up kind of thing. And so, of course, there's only one frequency here. This is not actually this is just a notation. This is the real frequency of this wave. There's no other wave with another frequency here. We must have a driving force. So we'll put it as, so this. Now I'm going to write it like this because in the book they do. You could easily just write cosine omega prime t. Omega prime I'm using for the driving frequency. So omega prime is driving frequency. And by units, that's its frequency. Well, whatever. By units, of course, this has no units because it's exponential or something. So there must be units of some force here. But that's fine. And now this is a damped driven harmonic oscillator. We could actually set, if we want, we could set gamma to be 0 and we would just get a driven harmonic oscillator with no damping force. That's fine. They don't even talk about that in the book because it's just a special case, right? It's just when, and also if you're talking about a driven oscillator, you're probably talking about something in real life. And in real life, everything has damping. So generally they would talk about this. So anyway, then they get some equation for x of t. And it has something like this. Okay, actually, you know what? Let me just look because I actually do want to get this right.
Yeah.
Normally I don't really care, but yeah. Yeah, so last time I mentioned in I think it was the last office hours, I'm not sure. It wasn't very long, I think, but I mentioned, so on page, I'm saying this for the video, on the page 94, right before equation 6.8, it says the advantage of the complex exponential is that the derivatives all have the same e to the minus I omega t factor, which can be canceled out. So I made a big deal last time about how it was nice to use that, and then for some reason I confused myself.
Yeah.
Basically, because it's an e to the something, we can always cancel it. That just assume that's true. Of course, if you're worried about the fact that e to the I times something sometimes is 0, I agree that I'm worried about that, but it all ends up working out, so don't worry. We're physicists, so we don't care about these math things. I'm gonna write exactly what they do.
Yeah.
Okay, so this is exactly what they wrote. This is equation 6.8. And I'm using the correct notation, not the notation they use in the book, which is very inconsistent between what I've written already. They call this omega naught again. I'm not going to get into it. But anyway, so this is not the full solution. This is just the amplitude. So remember, the wave looks like this. Okay. Actually, I believe it's a little more complicated, but don't worry about it. The point that they don't worry about it. That's why I'm not worried about it. The point is that, sorry, I just realized you can't really see this. Okay. So this is, you can see if you just divide everything by m, which is what we've been generally doing to get something like this and to get this gamma, divide this by m, then it becomes, if we just plug in the form of omega that we've had or whatever, we get basically the same type of form, but we have the coefficient, d, is actually dependent on omega. We get this factor in front of everything. Okay?
Yeah.
So don't worry about this, because if you look at the whole form, it's going to be really confusing. And that's why they don't write it in the book. But the coefficient is what's the important part. The coefficient is the amplitude, right? So this is still the amplitude of the wave, okay? And for resonance, that's actually all we care about. So this number up here is a constant. It's positive. I guess that doesn't really matter, but it's a positive constant. That doesn't change. Omega is dependent. Now, what is omega? Well, it's the solution to this, actually, which is, so omega is, it's like k over m, square root of k over m minus, whatever, something with gamma minus I gamma over, something like this. It doesn't really matter. The point is that this is dependent, just like I was saying, omega naught is dependent on k and m, which is just the system on its own. It has nothing to do with external forces. It's just the intrinsic property of the system. So does this. This is omega. It just has to, the drag is just the other parameter. It only depends on k, m, and gamma. Those are just like things about the world that you could measure, like the mass of the block you're using. It has nothing to do with waves for now. But, so that is sort of I don't want to box everything. It doesn't mean anything anymore. Okay, so this is the frequency that the system sort of wants to oscillate at. If you flick it, or whatever, it's a block, right? If you flick it, and then just watch it go, you don't give it any more input, it will oscillate. We just saw the wave, it will trace out at this frequency. So this is called the resonant frequency. Now the reason it's called the resonant frequency is because omega prime is under your control. It's completely separate. It's a new input because you're inputting this, just like F is a new input, but it turns out F doesn't really matter for anything. Omega prime is the new input. It's basically like if you're shaking it. What speed, what frequency are you shaking it at? And if you shake it, and you can see that if you shake it at some frequency omega prime, the amplitude will scale depending on that frequency. So that's fine. But of course, then what happens, let's assume that gamma is small, because if gamma is large, that means there's a lot of friction and nothing really interesting happens. So assume gamma is small, which means roughly, let's sort of ignore this term. So this means sort of roughly it's frictionless. Okay, now you'll see why that's impossible. Let's ignore it for now, but we'll remember that it can be very small. But in comparison to most things, like these are very big compared to this, let's say. So they're just sort of, but you can see that this can be 0. There's a minus sign here. This can be 0. Now, if this is 0, well then this, even if it's really small, it doesn't matter, because if it's 0, this will be infinity, and that's crazy. So what happens when this is 0? That means, so when this is 0, that means the amplitude blows up. So when omega equals omega prime, right? Or of course it could be minus omega prime because they're squared, but that's just sort of out of phase with, same thing. If the driving frequency is the same as the frequency it wants to oscillate in, then you get that the d goes to infinity, the amplitude goes to infinity. Yeah, so this is called resonance, right? The idea that, and you don't even have to be exactly there. If you're very close, it will still go up pretty significantly. It's not like just when you get to that point. If you're very close to that frequency, this denominator will be very small, and therefore the whole thing will be very large. And remember, this is all multiplied by the wave, by this.
Oh yeah.
So this is just the coefficient, the amplitude of it. So it's still going to oscillate. It's not like it's going to blow up and do something else. It's still going to go up and down. It's just going to go up and down with this amplitude, which will go to infinity as these approach each other. I really should say as omega prime approach. This is a more physical way to write it because omega prime is the thing you can control. You can't really control like the mass of the block you can't turn up the mass, right? It doesn't make any sense. So you can turn up the driving frequency, though, assuming that's generally what you're in control over. So as omega prime approaches omega, the amplitude goes to infinity. And again, so in other words, well, okay, yeah. Again, it's still a wave. It doesn't do anything. It's not like this is a new equation. This is just the coefficient of this equation. So, and they put like some tildes somewhere. They might call this omega tilde. I don't know.
Yeah.
Yeah. Okay. Yeah. So they call this omega tilde squiggle or whatever in the book. But anyway, I'll call it omega prime for now. Yeah. Okay, and then you'll see that of course if that's what I was saying, but if gamma is literally equal to 0, if there's literally no friction, it will actually be an infinite amplitude. Now that's a little bit crazy. Now, how could it be an infinite amplitude? Wouldn't that suggest there's an infinite amount of energy? Right? Because remember, if we use the potential energy from a spring, it's like 1/2 k x, and if x is the amplitude squared, then if this goes to infinity, this should be an infinite amount of energy. Where does it get the energy? Well, all it means is that every time you shake it back and forth, it's actually all the energy you're putting into it. The energy is coming from here. You're putting energy into it by shaking it. It just means that it's keeping 100% of that energy. So each time you shake it, it's just getting that much more energy and that much. It's never giving any of it up, right? It's never settling into equilibrium. Anyway, okay, I don't want to keep. This is very interesting, but I fear that you don't need it as much as I'm talking about it. I do think you need to know this fact and what this expression means. But you don't worry about the energetics of resonance. But what they were asking about is if you have two springs in parallel and series. So that's actually a separate conversation, and we'll come back to this. So I'm gonna okay, I'm gonna erase this for now. I'll write it later.
Okay.
And let's just start talking about springs in series and parallel because that's a little bit complicated. So a spring has a spring constant, so this is like m, it's fixed. Spring has a spring constant k, and k is, well, remember f equals minus kx. That's the definition of, well, I don't know what the spring, maybe, I don't know. It's called Hooke's law. And so therefore, you can measure k by saying, well, if I have given some force F, I should just say F. Given some force F, if I measure the distance that it displaces, well, it's of course going to be a negative. It's going to go in the opposite direction of the force. So it's going to be a negative number, but I just put the negative here and I get a number k, which has units of newtons per meter, right? It has to be newtons per meter because of this. Now, what if I put two springs, one spring 2, and let's say this has constant k1, k2. So this is two springs in series. Now, if you know about circuits and stuff, and series and parallel are very suggesting of what's happening here. And remember, so this is another way you can figure out what I'm about to say is remember, I talked about circuits, how circuits have the same differential equation. And if you just do some replacements between capacitors and springs, where 1 over the capacitance is equal to the spring constant, I think this is true. I'm not 100% positive about this fact, but I believe it's 1 over the capacitance of the capacitor corresponds to the spring constant in the. Yeah, I believe it does because if this is charge, voltage is charge over capacitance, I think. So therefore, this would be Q over C and this is all voltage equation. Anyway, therefore, if you know how to add capacitors in series and parallel, you should know how to add K's. You just put the 1 over. Anyway, that's just you could try this on your own. You could probably look up a derivation of that. I'm not going to do it that way because I'm not going to assume people know about capacitors because, to be honest, I don't remember anything about them. So something about 1 over C, I don't know. I don't really remember. We can figure this out this way. What is the net spring constant, K net, for this total spring? It's two springs in series, right, stacked. Well, if I stretch this a distance x, if I give this a force x, sorry, I should say force. If I give it some force, now k net is going to be, if I give it some force, what's the net distance I go, right? Sorry, let me erase this. Let me not make it so confusing. So this is the definition. This is how we find k net, right? If we give it some force, what is the total distance it goes? Well, I could write x net as it's just x1 plus x2, right? And I know that I'm kind of running out of room. Hold on, I'm confusing myself. So therefore I can write, let me write it like this, minus f over x1 plus x2 is k net still. And now, well, okay, well now this, oh, here we go. So now this I need to write in terms of something with just x1 and just x2 because I have k1 and k2. I know that k1 is f over x1, and I know that k2 is f over x2, right? And so I need to write this as two separate things. Well, that's a little bit complicated because it's in the denominator. We can't just separate it easily. We could multiply the top and bottom by x1 minus x2, I guess. That's not going to help anything. I mean, yeah, that's not okay. Well, I believe the answer. Okay, well, I'm pretty sure the answer is this. I'll let me write the answer and then I'll look it up, which is probably not the order I should be doing it in. Okay, I'm pretty sure it's like this. So in other words, this is just like if you about electronics, resistors in parallel add like this. The the equivalent resistance from two resistors in parallel look like this. Also two capacitors in series. Now I'm getting confused. I don't think that's right.
Yeah, and I forgot everything.
Hold on. Yeah, actually.
Capacitors.
All right. Let me just look this up. Springs in parallel.
Okay.
I will edit this out of the video so it looks like I know what I'm talking about. Okay, actually, yeah, there's a... No, okay, I was right, but I didn't say it very well. Well, there's a Wikipedia page called Series and Parallel Springs. Oh, they just write it. Okay, this does a way better job. So you can see... Sorry, you'll be on the video. I can edit you out if you want.
Yeah.
There's a derivation... Yeah. Actually, let me open this. There's a derivation of... Yeah, I'll link to this.
Okay.
Yeah, so what do they have? F. When pulling strings from equilibrium at the end of a block. Yep, totally. Yep, yeah, that's what I wrote. Yes, so they have that. X1 is F1 over... Oh, okay. So they have this. Oh, I guess they just... So it is just equal to this.
They forget the other steps.
I don't think they have the other steps either.
Oh.
Substituting x1 and sorry. We can substitute. Okay. We can do this way. All right. If we substitute those in here, it should work. Okay. Let me just make sure that. Okay. I think I can figure this out, but this is the right answer. But according to Wikipedia, so we have minus f over, and now x1 and x2 are just given by this.
Yeah.
We could write on the Wikipedia they write f1 and f2, but they're all equivalent because it's the same force. The force on all of them. And so we get x1 is f over k1. Yep. plus F over K2, K net. Well, I don't want to write K. It's all equal to K net. And now, of course, we could just cancel, divide the top and bottom by F, and we get minus,
One.
I guess these are all minus. Yeah, sorry. These are all really minus F. So we divide everything by minus F because we should have that. This is just being, we could just say that X is a negative displacement. We wouldn't have to worry about the minus signs. But so divide everything by minus F and we get 1 over K1 plus 1 over K2. And if this is equal to K, sorry, this is not negative. If this is equal to K net, just take the inverse of both sides and you get the equation I was just writing. So this is how, so this is the same as capacitors in series. The reason I'm pausing is because if it's capacitors in series, I thought capacitors in series added like this, but then the statement I made that K was the inverse of C is not true because that's not how, okay, don't worry about capacitors. Somehow I'm misremembering all of this stuff about capacitors, so don't listen to anything I said about capacitors. But this is definitely true for spring constants, okay? So you could say some stuff about this such that, like, the one thing I want you to be thinking about when you think about these two springs is that it's somehow easier. So this number is actually lower than these numbers, because like you sort of want so K is kind of like how stiff is the spring. If you have a very high K, it's very stiff, right? Because K is really K is really like if X was very small, if it didn't move very much, this number would be large, and so it would be very stiff. That's high K. If you stack two springs and you apply the same force F, only sort of, it's kind of like you can imagine, well, part of it's going to one and part of it's going to the other. Not part of the force, but part of the stretching. So each one actually doesn't have to stretch as much. So therefore, it acts like a spring with a lower spring constant.
Oh.
Does that make sense? It's not like they stack, right? It's not like they stack and you have to stretch both. You don't. You have to stretch. It's kind of like if one's really easy to stretch and one's really hard, pulling it is actually going to be still really easy because the easy one's just going to stretch most of the time. And then even it's actually going to be easier than that because the easy one by itself has some spring constant. But if you add the stiff one, well, that can stretch a little bit. So it's actually going to be easier than both of them. So that's the conclusion. This equation is kind of hard to parse, right? But really what this is saying is that two stacked springs is easier to stretch than either one separately.
Oh.
And it's because of this. And you can see if you plug in anything for K1 and K2, K net is always smaller than both K1 and K2. At the worst is if you set one of them to be, well, okay, I'm not going to worry about it. You can't set them to be 0 anyway, but okay, never mind, forget it. The point is that it's always easier than either one, and it's because, just imagine, stretching one has some difficulty, but if you just add anything else that stretches, it's going to be easier. It might not be that much easier, because the other one might not help much, but it's going to help a non-zero amount. So that's kind of a good, that's the way I think about it. Whether that helps you or not, if you just like this equation, that's fine. I personally don't see that, this doesn't mean anything to me.
Yeah,
it's just like, all right, it's some inverse thing. I mean, I guess you could think of it here. I'll stop. I don't want to keep talking about things that you don't need to really know, but you could think of it like this. This is the way I wrote it originally. This is the same. Now you could think of this as something adds, right? But it's not the K's, it's the inverse K's. And if K was the stiffness, then K inverse, you could say, is the stretchiness. So the stretchiness adds together perfectly. That's one way to say it. Now, we don't, in equations, we never use stretchiness. We use K. So if you want to call K inverse stretchiness, that's fine in your head, but you shouldn't do equations with it because that's just it's a convention. We could use the other one, it would be just fine. With capacitors, we actually do use the other one. The capacitance is okay, I'm going to say something wrong about capacitors. I don't want to keep doing that, but anyway, and so now let's talk about, I didn't want to raise this tip. And now let's do springs, sorry. Went to a string theory talk, so now I want to say strings. So we have And now it looks much bigger. I don't mean to I don't mean to say it's much bigger. It's the same mass. But we have K1 and K2. And now they're in parallel. So this is parallel springs. And now, of course, K net, I might have used K equivalent at some point. No, I didn't. In electronics, you would call it equivalent because it's sort of equivalent to one spring with that spring constant. And so K net is going to be, well, it's just going to be the total force you apply over X. Well, I mean, this is kind of simple because the total, it's kind of like you can think of it, the total force you receive is just going to be the force of both, right? Like what net force will let's compute instead the net force you'll get from both springs. Well, one spring will give you a minus K1x, if you compress at a distance x, I should say. And the other one will give you a minus K2x, right? If you compress this a distance x, you'll get this force plus this force. It's just the sum of the forces, right? There's two springs on it, so there's two forces. But now if you think, therefore I applied a force, F, I received a x distance displacement. What was, now this is just, of course, this F is the same as the F net I was just talking about. And so you'll get minus K1 plus K2. Well, this is just a spring with K net equal to K1 plus K2. And that's a much easier equation to visualize. And this is actually even much easier to imagine. Just imagine put two springs. If they're, let's say they're the same, just to make it easier, they're the same spring constant. It's just twice as hard to push because there's two things that are opposing you. This is very intuitive. This is a little less intuitive, of course.
Yeah.
But but this equation is not easy to imagine what the behavior is. This is much easier to visualize. Even if one of them was very, very stretchy, doesn't matter much, well, then it basically behaves like that one other spring. So imagine this one goes to 0, well, it's still just like the other spring. Nothing crazy happens. If they're both exactly equal, there's just like it's like a spring twice as much spring constant. So this is parallel springs, and this is series springs. Okay, now, so that was all that. Now I think that's prerequisite knowledge because they don't even say anything about them. They assume they want to know the effect of the resonant frequency. Oh, and then if the mass is doubled. So they're asking about the resonant frequency omega. Now the resonant frequency, remember, was in that equation. It's just the resonant frequency is the same as just let's just say it's k over m. I'm doing the special case when gamma is 0. If you want to do the case when gamma was not 0, you just write. I don't remember the formula, so you just write it out. It doesn't actually change anything significantly.
Okay.
All they want you to do is say, when they say resonant frequency, they want you to, of course, you're going to think about resonance, but it doesn't really matter because the resonant frequency has nothing to do with the input. It just has to do with the what's in here. What's the system made of. So the system is made of K and N, and gamma perhaps. And so if you connected two springs in series, what will happen to the resonant frequency? Well, I think they just want you to say if it'll go up or down, right? Sorry, I keep looking at this and then not remembering what it says. Yeah, what is the effect? So you can just say if it'll go up or down. I mean, yeah, you can just say because they don't give you enough. They don't tell you what the springs are, their spring constants or anything like that. So we don't actually know how much it goes up or down. If we added another spring in parallel, right, what would we get? Well, it would just behave like, that's it. Sorry, squared. This is what I meant. So therefore, the omega naught, the actual resonant frequency, would go like, right? So it wouldn't, now if they were the same, like let's say you added another exact copy of the spring, this would be 2K, and this would be 2K, so it would go up by a radical 2. Okay, now that means it goes faster, right? Because if the frequency is increased. Anyway, so the period would decrease. Another way to say it. They don't ask you about any of that, but that's just how it goes. So that's fine. Now, if they said they're in series, well, we use this one. And if they're in series, well, again, it's a little bit hard to imagine to see like what is going to happen. But I've told you that this number k net. So for springs in series, k net is less than k1, and k net is less than k2. This is just a fact about this equation. Any k1 and k2 and k net that satisfy this equation have this property. So this is quite the important property. This is the equivalent to saying two springs in series are always easier to compress than either spring on its own. Now, of course, from this, you'll see that whatever it is, whatever my new k net is, if it's made of some complicated thing, it's just going to go down. So my omega is going to go down. That kind of makes sense, because if it went up with parallel, it's probably going to go down with series. That's usually how they ask those questions. Now, the other thing is, what if they added mass or reduced mass? It doesn't matter. Well, what does that do to the resonant frequency? You can just see what happens. If you decrease the mass, you're going to get a higher resonant frequency, and if you increase the mass, you're going to get a lower resonant frequency.
Yeah.
That makes sense. So I know we spent a lot of time on this problem doing things that didn't seem like they were really, about waves, but I don't think he'll ever talk about this in class, and the question assumes that you know it. So I want to make sure that it's somewhere so that you can look it up or at least see how to get it.
Yeah.
This would be a good problem for the quiz, honestly. I'm not saying there's a hint. I literally have no idea. I've never seen it.
Yeah.
So I don't know. But I just mean this would be a good problem because it's relatively simple. I mean, but even though I had to look it up, it's relatively simple because you just have to. It's just some algebra, knowing algebra stuff here, and filling in this. It's just Hooke's law, and then sum of the forces kind of thing. That's kind of all you need to know. It's just a little bit counterintuitive and get a weird equation. But anyway, so does that make sense?
Yeah.
Okay.
It was really clear for me.
Good. Okay, and then the 6 was okay, so yeah. So this is about, so now I'm not going to fill in the numbers because as usual I find them very boring.
Yeah.
And I just get lost, and I hate numbers. So I'm not going to do that, but I will just talk about the parts that you need and the parts that you don't need. Now, you do need to write the whole equation out because I think that's what they're asking for. The thing is, you don't really need to do anything with it because what they want to know is you have some oscillator with, and now it's a damped oscillator, so we know, sorry, should use D. D, E to the, needs to be cleaned or something. It looks kind of like this. This is just schematic. I don't want to say exactly. This looks kind of like this. Maybe you can fill in the phase from what they said. I don't really care about that. What's that? Oh, sorry. Thank you. I always forget that. Okay. So now we know that if they're asking about the amplitude, like when does the amplitude drop to whatever, the amplitude is just this. Well, it's D times this. Actually, I really should say D times this. So it's D times, now this formula has, well, this is D. This equation is D e to the minus gamma over 2, gamma t over 2. And then, of course, it has the negative version to the other one. But this is the amplitude. And now we actually don't even need to plot the actual wave. This actual formula is given by an oscillating wave, but this thing is just the amplitude of the wave. And if they're only asking about the amplitude when it's decreasing, that's actually a question just about this function. So when they say, when does it, yeah, okay, good. If the initial amplitude is 20 and falls to half after 6 oscillations, okay, so I guess it's a little more complicated than I thought. If this falls to half, now they say it's 20 at the beginning, so I guess you could say D is 20 because at t equals 0, this is all 1, and this becomes 20. Doesn't really, of course, doesn't matter what the number is because this is just going to be D over 2. So when is the amplitude half? Well, that's when if we use this is the formula. We want to set it equal to some value. We want to solve for t. Right? Does that make sense? This is the whole amplitude. We want to find the t such that it's equal to d over 2.
Oh yeah.
So we've reduced. This is a very complicated. Now you should do when you do the problem. You should fill it in as you should, as you normally would with a wave equation. Don't just skip right to this. But this is essentially the problem they want you to do. And of course, the d's cancel. This is like a half-life problem. If you've ever done any of those, this is like this. And now you can see it doesn't even have anything to do with d. That's why I said it doesn't matter. I told you it's 20. It doesn't actually matter, of course. If you put in 20 centimeters and 10 centimeters, you still get a half. Take the natural log of both sides. I'm just so this on it. And then the natural log of this is minus gamma t over 2. And the natural log of this is ln of, well, I'll say it's minus ln of 2. I'm skipping a bunch of steps, but that's how logs work, right? Now they're both positive. And now 2 ln 2 over gamma is t. Okay, now I'm, again, skipping a bunch of steps. Please, please, when you're doing this, do all the steps. At least do all the steps you need. If you follow this perfectly, that's totally fine. But now this expression, you should not memorize this, but this will come up a lot. It's called the half-life. The half-life. Well, depends on how you define. Sometimes they don't put a 2 here. I'm just putting a 2 because I thought that's what they did. But if they don't, you just won't have a 2 here, and you'll get ln of 2 over gamma, which is called something's called the rate or the decay rate or something like that. This is called the half-life then. And it will be the time it takes for this exponential to decay by half. It doesn't just have to do with radioactivity. It has to do with anything that follows this decreasing exponential, which is a lot of things, as we saw, because it comes from a differential equation. And most things in nature come from differential equations. So this shows up a lot. So anyway, it's called the half-life. It's actually called twice the half-life. And so then they say, so we have the expression for the time, but they say it fell after, so I guess we don't have gamma, I think, because they told us to find something, right?
Yeah, we didn't have to.
Oh, calculate the damping coefficient, alpha. Okay, so they're calling, So alpha, the gamma is the same as alpha, because they say that the drag force is proportional to, this is what they say, and now this is exactly the form that if you put gamma in here, you get this equation. So they use alpha for the question for some reason, but whatever, it's the same thing. So now we don't have alpha or gamma, right? The same.
Yeah.
We don't have gamma. I'm going to start saying gamma. Therefore, we have it in terms of some time, but this is the time for it to decrease to half. Oh, so I guess we could solve it, but we still, of course, this time doesn't necessarily relate to. We don't necessarily know about the oscillation. So we'd have to do some computation between the oscillations, which is, I guess, the period, and the, so like if let's say it looked like this.
Yeah.
If we have 5 oscillations, this is the time for 5 oscillations. And remember that t, so I don't exactly know how to do it, because I would have to sit down and do it, but these are definitely all the pieces.
Okay.
Again, there's another reason I don't want to go through exactly the problems, is because then if he asks you a slightly different problem, he's going to think, well, that's an easy one because it's slightly different from the homework. And if you're sort of, sticking too close to like there's one thing of following a question that's on the homework versus like constructing it from just a little bit more general version. That's actually, I think, a lot more helpful. Well, I know it sounds like a very teacher thing to say, but seriously, I think it is. So this is like 5 oscillations, for example. Now they say 6 or whatever, so 6 oscillations, but we have to convert between this time and whatever time we had here. And remember, t is, I think it's 2 pi over omega or something like that. T is really 1 over f, the frequency, and it's related to omega. I believe all of that is right. So omega is the angular frequency, 2 pi is the number of radians in a revolution, and f is the frequency of a revolution, like having one revolution in how many seconds, kind of thing. The t is the answer to that question. And so you can see how this, which shows up here, right, can relate to the period, which relates to the time for some event happening, and therefore it relates to the decay through this thing. Now this doesn't have to be, they said half, but if you wanted to say, well, let's say I knew sometime. Let's do this slightly differently. Let's say I knew. So this is the same equation, but let's say instead of this, I wanted to find this. I said I knew sometime. Let's say the time of 5 oscillations, which is this, which I could also. So let's do this question. I'm making up a question. What's the amplitude after 5 oscillations? Right, so I know, now I could take the time for 5 oscillations. Omega we can compute from just the square root and the k over m, all that stuff. So we know that 5 oscillations would be therefore 5t. So time for 5 oscillations is 5, I'm just writing it the other way, but 5t, which is 5 times 2 pi over omega, right? So supposedly omega we can solve using the information they gave you. So I'm just pretending that, I know this isn't the exact problem. And then this is therefore 10 pi over omega. So this is the time. Now I want to find what's the amplitude then. So I'll call it A for, yeah, I'll call it A, I guess. Well, now I can actually just plug in t at 10 to the power of 2 over 2. It gives me the amplitude at any time. That's what the point is. And this will give me some amplitude A. Now, what if I didn't know gamma too? Well, then I actually don't have that information. So I would need another fact, which is that at some other time, let's say at some time t for 10 oscillations, actually that's stupid because that's just twice this. Okay, let's say, I don't know, t1, let's say they give you some time and they say that the amplitude is halved. So they give you the half-life. So I'm just basically rewriting. They give you the half-life, that means the amplitude is half of what it was, and then we could do, it's just the, sorry, I shouldn't have erased that then. It's like, I'll say 1/2. This looks much more confusing than I meant it to be. Yeah. Let's call it T1. Let's say they said, using this, if they gave us this time, we can solve for gamma. And we can also then later plug in this same equation for the amplitude for a different time, once we know gamma. Does that all make sense? I know I'm just saying, it sounds like I'm saying random things. Like, I'm scattering random. The point is, there's many questions you could ask about this type of thing. This is literally just a question about, that relates, this is a question about this function, e to the minus something, t. Okay, that's literally, all this is just about that function, which is, in this case, the amplitude. And then occasionally they relate it to the angular frequency, which comes from, well, it's from this part, but it's, we have all these equations for it. We have, square roots and whatever, minus 2, whatever we get. We have all these equations for omega. So if we needed to find that from other information, we could. So I would say with this question, try to set up everything like this that you can, and yeah, and then essentially the end point of the problem is going to be of them asking questions about this, the amplitude, which is just given by an exponential function, and then that's essentially questions about an exponential function, which are relatively simple because you can always do something like this, ln of thing. That's the tricky part. But then now you just have equations with two unknowns, and maybe you have 2 equations, 2 unknowns. I don't want to give too much away. I don't want to say anything that's too explicitly equal to the answer. Of course, I'll be here this Saturday. So if everyone's working on it, I can go over it. But anyway, okay, does that make sense?
Kind
Do those pieces make sense? Okay.
Yeah, it's kind of.
Hopefully with these pieces, once you sit down, this is probably a very long one.
Yeah.
Also, so I would say once you sit down and, start doing each piece, hopefully the pieces you know already, and these pieces will be enough for you to put together the whole thing. That's my goal in this, is to give you all the pieces so that you're never, if you're stuck because you don't know, you've never done this problem before, that's kind of not helpful for you to be stuck on something you've never seen. Whereas if you've seen all the pieces and you're just struggling to put them together, that's actually a good thing. So, Okay. All right. What else?
I think.
Oh yeah. So we have time, but I sorry, I've been talking too long. I didn't really say anything about waves yet, but
Well, I think we have something about waves
yeah.
because definitely when I start doing something, then I'm going to have more
Yeah.
questions. Right now, it's like
Yeah. Oh, also, I'll just say one quick thing about Part B. So Part B asked you about the energy lost. The
Oh, yeah.
energy from in this wave is always 1/2. Okay. Yeah. Let's just say this. Yeah. So the energy is always 1/2 k times d squared. Now d is the amplitude. Okay. It's
Yeah.
not always. It's not this. Sorry, I shouldn't say that. It's not the right. It's 1/2 k times the amplitude squared. Now the amplitude is this, which is, I mean, this is correct. The amplitude, of course, decreases over time. So the energy does decrease over the time, right? So if you know, so of course it's oscillating. So it would be, you might think, oh, it's complicated because, sometimes there's a bunch of kinetic energy and sometimes there's a bunch of potential energy. Well, yes, that's true, and that's in general kind of hard. But when it's at the top or at the bottom, all the energy's in the spring, right? There's no energy from, nothing else is happening, there's no velocity, so there's no friction energy like from the drag term. It's all in this form, and this is the energy of a spring is 1/2 kx squared. X is at the total amplitude. So if you know the amplitude at any time, which you do because it's this, you get the energy at that time. So this is all a function of t. T meaning time, right? So therefore, when they say how much energy is lost, well, if you know the initial amplitude and you know the amplitude at whatever final point you get after doing part A, you could just compute them and subtract them. So anyway, that's just that part is much easier.
yeah.
The first part might involve you setting up the whole equation, but okay. Hmm. Yeah. I just don't know what I can say about this. It's going to be because. So.
They are asking 1, 2, and 7. Maybe something that
1,
is-
2, and 7. Oops, sorry.
Let's see.
1. Okay, so they're asking about definitions.
Yeah.
That's good. Okay, I'll talk about that. And then 2 is. Yep. Okay. And then 7 is plot the wave that results from interference of two identical waves. Oh,
Some of them.
okay. Yeah, you could do it on MATLAB, or you could probably, well, yeah. 7 is actually not as hard as it sounds, I think,
Oh, okay.
because things that differ, 3 pi over 2, you could write it as just like, it's going to be something like sine plus cosine, plot sine plus cosine, with some, you'll have to worry a little bit about the 3 pi over 2 as opposed. If it said plot the interference of two waves, actually, well, okay, let's not worry about that for now.
Okay.
I would have to think about number 7 for a little bit, but as far as I can tell, it's easy, but I'm not positive. But number 1 is a really good one because it literally is asking you about. Yeah. So they're asking you basically about the parts of a wave equation. So a wave is slightly different from a harmonic oscillator. So that sounds kind of like a wave because it goes up and down, and right. But a wave is really, it's kind of like a harmonic oscillator at every point. So if you have a line with harmonic, a harmonic oscillator is kind of like a zero-dimensional wave. There's not really a reason I'm saying that other than because it sounds kind of interesting. But it's probably true, but it's a little silly. I mean, because the reason I say zero dimensional is because if you say there's no x and everything's just time, harmonic oscillator just goes up and down in time, right? Over time it goes up and down. Of course it travels over space, but there's only one point that actually is a harmonic oscillator. A wave has every point is kind of like a harmonic oscillator. So okay. So there is a phase, just like for the same reasons we've always had. I'm actually going to erase it because it makes everything annoying. Of course, this can also be written as e to the I kx. So make it t. Right. Of course, it's like real part, imaginary part, whatever. But let's just leave it like this. Okay. So what is k and what is omega? Well, omega is the same thing it always was. It's the frequency. And you know that because it's the thing that multiplies time to give you something with no units. You can't have any units in sine. So it has no units. So it basically gives you over t. Well, you know what the frequency is. Basically, how long does it take to go one? Really, this is how long does it go 1 radian, kind of thing. That's really 1 over omega. But anyway, k is slightly different. Now, k is just like that, but to x. So it's kind of like the frequency in space. So what it means is that how long in so a wave, let's actually define this a little better. Let's say this is our x position, and we have some wave like this, and it's traveling this way.
Yeah.
This equation is y, this is y, and this is x. Okay. Now t I don't show because I can't. It's in time. So forward in time actually moves this over, right? And so k, well, it's going to be hard to write because this, of course, you can't write just like a single sign. You can write it like a bunch of signs, which is the whole Fourier thing. But let's have this is a standing wave. It's going to be a little complicated, but let's say it's a wave that's sort of oscillating up and down. There's a node here, and yeah. So now I'm going to risk saying something wrong, but I believe this standing wave like this is given by so he was saying that it's like two waves traveling in the opposite directions. So this sign here, the reason it's plus or minus, is because one direction, when you evolve forward in time, you go in the same direction as x. And in the other one, you go the other direction. So I don't really know a good way to say that other than if you think about like stepping, like t goes to the next period in time. If t goes to the next period in time, what's going to happen to this? Well, if you know what? Okay, there's not going to be a good way to think about it. If you sit and stare at it for a few minutes, you really can see why one of them is forward and one of them is backwards. If you just imagine, well, if t goes forward in time a little bit, what happens to this argument? Does the amplitude go up or down? And then what has to happen to x? Where do you have to shift x to get it to be the same? That's kind of the direction the wave's moving in because you're shifting x. But anyway, that's all sort of a not very helpful thing to say, I guess. But yeah, I mean, so this is called the wave equation. It solves the differential equation. Yeah. Yeah, I'm not totally sure what.
I mean, I can break it up, but again, like if you sit there and like 2 hours go by, so you have to.
Yeah. Okay. They kind of have a little explanation of what I was just saying on 103. Yeah, they kind of describe how it's moving a little bit. Well, Yeah, I guess another thing I could say is if you want to find the transverse velocity, so the transverse velocity is the velocity of okay, let's just say this. Imagine you have a wave like this over space. This is the height y. Now, if you imagine, okay, well, I have a wave and it's moving this way or whatever, I have both waves, doesn't matter. Nothing's, of course, moving to the side. There's no mass that's moving to the side, right? Everything's moving up and down, right? So the transverse velocity is going to be the actual speed of the particles on the wave moving up or down. And of course, that's dependent on a lot of things. You can figure it out by just saying, well, if I say x is x naught, I actually sort of want to send x to x naught, meaning this is a constant now. This is, of course, this had variables in it. But if you set it to be a constant, well, you get y x t is a times sine. Now I have k x naught. Let's just say it's plus omega t. Now this is a constant, so this whole thing is really like a phase, right? Because it's a constant thing, so that's fine. Now the velocity downward is going to be, well, it's dy dt, right? So this is the transverse velocity. Because it's the dy dt is just velocity in the y direction. That's literally, you pretend, not even if nothing is here, dy dt has to be the velocity in the y direction. Therefore, if we pick some fixed, and of course you have to pick some point, so if we pick some point x naught, and we plug it in, we will get just the motion of a single point. So now this is actually y of x naught t. This is the motion of a single point at x equals x naught, up and down in y. And so if we want the transverse velocity, that's just dy dt, so we can just take dy dt, which is going to be a omega cosine kx naught plus omega t. Now, of course, the velocity is going to change over time, we see. And of course, that makes perfect sense because up here, it's going to be zero velocity and down here, right? But if we say, what's the maximum velocity, let's say, which is right when it goes through the center, right? Pretend this is the center, whatever. This is going to be 1 at max, and you get a omega. So you can see that it looks just, and this looks just like, if this is a phase, this looks just like a harmonic oscillator, right? This is exactly the same as a harmonic oscillator. If we replace kx naught with, which is a constant with just a phase, we get exactly a harmonic oscillator. What that's saying is that every point behaves exactly like a harmonic oscillator, which is sort of what I was saying before. So in other words, when we were, by setting x to x naught, we're reducing the x dimension to just a single point. So we're sort of collapsing one of the dimensions. If this is a one-dimensional wave, so a harmonic oscillator is like a zero-dimensional wave. That's just the cool. I just wanted to mention that cool thing. So in other words, the reason I'm really saying that is because I don't want you to think of, well, there's harmonic oscillators and there's completely separate things called waves which are complicated and have many terms and stuff. All we're doing is just adding a space term, right? All we had before was a time dimension. Now we have a space and time dimension, right? So the waves are actually just describing a harmonic oscillator at every single point in space, such that over space they actually end up being a wave too. You could write this, now there's different differential equations that you could write as like, you could write like this. Now, depending on, if you know your sine and cosine, sum of angle formulas and all those, now I don't remember any of them at all. But if you look them up, and I think they talk about them in there somewhere, I don't remember where. I thought I saw it somewhere. I don't remember, maybe it wasn't for this reason, but you can break up, sometimes you can break up sine of a plus b into something like this, with some there's some, of course, rules and stuff about it, but this is much easier to see. This is literally a wave in x and a wave in t at the same time. Now these are similar. Now these are not equal to each other, so don't write that down. But there's some rules you can do to convert between these. This is, I think, easier to see why it's literally just adding another dimension, right? Saying it's also a wave in space too. This is actually easier to deal with because you can do things like find the velocities of the waves and stuff like that over distance, which we'll talk about in the future when I look up a good way to explain it, because I don't remember. But and then of course you can use the differential equation to find the it essentially, I'll just say real quick, essentially comes down to I'm not. This is one of the equations I'm going to write that I have very little confidence in.
Yeah.
I have very little confidence in the powers and the powers basically of this. It might be v squared, or it might be 1 over v squared, or it might be 1 over v. I don't remember, but this is the velocity of the wave. And what it's saying is that it's relating my time sort of dimension, right? It's saying oscillating up and down in time with translating in space, sort of this is kind of like a curvature, but that's a whole separate thing. But yeah, this is not a very good explanation. Again, I'll have to look up a better explanation of why this is the velocity. Another place you could see this is in that electric field. So this is not something we need to talk about for now. But electric fields, if you know about electric fields, okay, I'm not going to talk about electric fields. Well, I'll just say real quick. Electric fields and magnetic fields have forms that look like this because they're waves.
Yeah.
And it just happens that if you have a electric field, if you have electric field by itself, it'll just dissipate. But if you have an electric field that generates a magnetic field, which they do if they're moving in a certain way, right? And then that magnetic field that it creates will, in turn, create an electric field. And if that self-generates, it will actually form a wave equation, right? You can describe with a wave equation, and this number that appears here will be something like this, which this is called the permeability of free space, and this is the permittivity of free space. So if you know about electronic, I don't know what field they use it in, but those things, you get something like this, and this number is the speed of the wave, and you get exactly the speed of light, because this self-replicating, self-generating electric magnetic field is literally a photon. That's what light is. So anyway, that's not a very satisfying thing, or probably very helpful for most people. But if you've seen these numbers before, they seem sort of like silly numbers that just go along with. They are silly numbers because they just measure them from the world, but they happen to produce the speed of light exactly because of this thing, because they produce a wave like that. Anyway. Okay.
Okay. Yeah.
Is that we started off good, but
Yeah.
I worry that we ended. Well, anyway, I'll come up with some more interesting, better, helpful things to say about waves, because you can get into very complicated problems very quickly, and I don't want to do that. Because I want to stick to the ones you need to know how to do. Okay. Do you have any questions?
I think not yet.
Okay.
I need to.
Yeah. No rush. There's no rush to have any questions.